Hello, I'm Münevver Topçu. Today I'm going to talking about presentation. The subject of the project is integrating core activities in the project life cycle. These are the topics we will talk about. I will tell about classic and other software development methodologies. The models represent the framework of a disciplined approach to development, have milestones, deliverables, constraints, etc. Software quality assurance must take place in conjunction with the completing of these activities or looking at the work products produced from these activities. Need to understand the models before we can produce plans that are integrated into these models. There are four models: software development lifecycle model, the prototyping model, the spiral model, and object-oriented model. First model is software development lifecycle model. The model displays the major building blocks for the entire development process, described as linear sequence. It's classic model. The most common illustration of this model is the waterfall model. Product delivered for evaluation and deployment at the end of development and testing. This is the waterfall model. The model shown in figure presents a 7-phase process. First phase is requirements definition. The customers must define their requirements. In many cases, the software system is part of a larger system. Information about other parts of the expanded system helps establish cooperation between the teams and develop component interfaces. Second phase is analysis. Analyze requirements to form an initial software model. Third phase is design. Detailed definition of inputs or outputs and processes, including data structure, software structure, etc. Other phase is coding. In this phase, the design is translated into a code. Coding involves quality assurance activities such as inspection, unit test, and integration tests. Other phase is system test. Goal is to discover errors or correct errors to achieve an acceptable level of quality, carried out by developers prior to delivery. Other phase is installation and conversion. After testing, system is installed and replaces an existing system. Requires software or data conversion. Important to not interrupt daily activities during conversion process. The last phase is regular operation and maintenance, usually done for years. Maintenance incorporates 3 types of services. These are corrective, adaptive, perfective. Second model is prototyping model. The prototyping methodology makes use of developments in information technology, namely advanced application generators that allow for fast and easy development of software prototypes. Active participation in the development process by customers and users capable of examining and evaluating prototypes. This is the prototyping model. According to prototyping model, developers build a prototype during the requirements phase. Prototype is evaluated by end users, and then users give corrective feedback. Developers further refine the prototype. Finally, when the user is satisfied, the prototype code is brought up to the standards needed for a final product. Prototyping as a software development methodology has been found to be efficient and effective mainly for small to medium-sized software development projects. Advantages of prototyping: shorter development process, substantial savings of development resources, better fit to customer requirements and reduce risk of project failure, easier and faster user comprehension of the new system. Disadvantages of prototyping: Diminished flexibility and adaptability to changes and additions, reduced preparation for unexpected instances of failure. Other model name is the spiral model. Uses an iterative approach designed to address each phases in development by obtaining customer comments and change, risk analysis, and resolution. The spiral model typically has a spiral for each of the traditional development phases. A heavyweight, plan-driven, highly structured approach for large projects, especially designed for those with higher chances of failure. Combines iterative model emphasizes risk assessment, customer participation, prototyping, and more. Definitely an iterative process. This is the spiral model. According to the spiral model, software development is perceived to be an iterative process. At each iteration, the following activities are performed: planning, risk analysis and resolution, engineering activities according to the stage of the project, design, coding, testing, installation, and release, customer evaluation, including comments, changes, and additional requirements, etc. This is the advanced spiral model. Other name is win-win model. The last model is object-oriented model. The object-oriented model differs from the other models by its intensive reuse of software components. This methodology is characterized by its easy integration of existing software modules called objects or components into newly developed software systems. This is the object-oriented model. Advantage of object-oriented model. The cost of integrating a reusable software component is much lower than the cost of developing new components. The integration of reusable software components reduces scheduling pressures. Used software components are expected to contain considerably fewer defects than newly developed software components due to detection of faults by former users.
Hello, teacher. My name is Rona, Emre, Altuğ. Today I'm going to talk about the chapter 7, 7.2. The name of chapter is Factors Affecting Intensity of Quality Assurance Activities in the Development Process. In Turkish, geliştirme sürecinde kalite güvence faktörlerini yoğunluğu etkileyen faktörler. Bu iki tür faktörümüz var. Bunlar ilerleyen slaytlarda var. İlk önce oradan konuşmaya başlayacağım. In this page, we are seeing that there is two factor. The first one is project factor, other one is team factors. Also, project factors include magnitude of project, technical complexity and difficulties, also extent of reusable software components, severity of failure outcomes if the project fails. Also, in this presentation, I have two examples, two scenarios. Also, we are going to talking about these factors, which is include, for example, magnitudes of project or reusable software components. How it affects our quality assurance activities. So other factor is team factors, professional qualification of the team members. Also on the other hand, team acquaintance with the project and its experience in area. Yani it means proje ve alandaki deneyimiyle takımın tanışmasından bahsediyoruz burada. Bu iki faktör, yani proje ve takım birbiri içinde uyumlu içinde olması lazım. Ve öte yandan tabii ki takımın bu alanda yeni ya da daha önce de tecrübeli bir staff mı, onları bilmemiz gerekiyor. Bunlar hep etkilen faktörler bizim quality assurance'ımızı. On the other hand, also availability of the staff members. who can professionally support the team. Also, the last one is familiarity with the team members. In other words, the percentage of new staff member in the team. Also, this factor is very important for us. So, in here, I'm going to give some information. In project life cycle, quality assurance activities are process-oriented. In other words, linked to completion of the project phase, accomplishment of a project milestone and so forth. Yani proje yaşam döngüsü, kalite güvence faaliyetleri süreç odaklıdır. Başka bir deyişle de bir proje aşamasının tamamlaması, bir proje kilometre taşının gerçekleştirilmesi vesaire hepsi birbiriyle bağlantılıdır. Bunu demek istiyorum burada. In this page, development models, the quality assurance activities will be integrated into development plan that implements one or more software development models. For example, the waterfall, prototyping, also spiral, object-oriented, and the other models. Also here we can see the other models. And in here, there is some determination. Quality assurance planners for a project are required to determine. So the list of quality assurance activities needed for a project. For each quality assurance activity has the timing, also the type of quality assurance activity to be applied. Also the performance, the activity and resources required. It should be note that various bodies may participate in the performance of quality assurance activities. Development team and the department staff members together with independent bodies such as external quality assurance team members or consultants. So resources required for removal of defects and introduction of change. Also, implementation tips. In some development plans, one finds quality assurance activities spread through the process, but without any time allocated for their performance or for the subsequent removal of defects. And also, someone maybe probably assumed that a late afternoon meeting would be sufficient for performing the quality assurance activities and the correction to be made. As nothing is achieved without time, the almost guaranteed result is delayed, caused by the unexpectedly long duration of the quality assurance process. Hence, the time allocated for quality assurance activities and the defect correction work that follows should be examined. Also, I talked about this page. Here is the factor affecting the required intensity of quality assurance activities. I already talked about it. I passed that page. And the following two examples, I'm going to illustrate how these factors can influence quality assurance activities. Also, here is two examples. The one of them is here. For example, a software development team has planned to quality assurance activities for its new consumer club project. The current project contract signed with a leading furniture store is the team 11th consumer club project leading in the last 3 years. The team estimates that about 7 man-months need to be invested by the two team members assigned to the project, whose duration is estimated at 4 months. It's estimated that a reusable components library can be supplied 19% of the project software. These sentences or this factor is very important for us. Next page, I'm going to explain that also the end of the second example, we can understand how it affects our assurance quality. So 3 quality assurance activities were planned by the project leader. The quality assurance activities and their duration are listed in picture. This picture you can see here is for example, the leader is planned that design review of requirement definition. We can see that in here this picture. Duration of quality assurance activity in 4 days is half day, for example. Duration of corrections and change 1 day. Inspection of design 1 day, also design 1 day. System tested completed software package. Its duration of quality assurance activity is 4 days. Also duration of corrections and change is 2 days. So in this example, the main consideration affecting this plan are, for example, degree of team acquaintances with the subject, also high percentages of software reuse. For example, for this scenario, it say that reusable components library can supply 19% of project software. So high percentage of software use, size of project in this case are medium. Also severity of failure result if for example there are the severity of failure results if the project fails. So second scenario, this scenario is a little bit long, but we are going to compare these 2 examples and we can understand how these factors, how it affects, and we can see the result. In this example, the real-time software development unit of a hospital's information system department has been assigned to be developed an advanced patient monitoring system. So the new monitoring unit is to be combined of patient room units with a control unit. The patient room unit is a mean to interface with several types of medical equipment supplied by different manufacturers, which measure various indicators of the patient condition. A sophisticated control unit will be placed at the nurse's station with data to be communicated to cellular units carried by doctors. Also, the project leader estimates that 14 months will be required to complete the system. Also, a team of 5 will be needed. These factors very important for us. It says 14 minutes, for example. Also, a team of 5 will be it says needed. Also, with the investment of the total of 40 months, she estimated the only, for example, 15% of the components. Also, we said the components we talked about can be obtained from the reusable components library. The components can be obtained from the reusable components. It's about the reusable components. 15%. Also, the SDLC methodology was chosen to integrate application of the 2 prototype of the patient's room unit and the prototype of control units for the purpose of improving communication with the user and changing feedback to comments at the analysis and design phases. So, as a result, the main consideration affecting this plan are the high complexity and difficulty of system. Also, maybe this scenario, the project size may be bigger than medium. We can say that low percentage of reusable software available because of it say that just 15% is components are reusable. Also, it say that it's here as I said you, it's bigger than medium, large size of this project in this case. I can write here, in this case, it's large. Also, in here, for example, this one, the failure results like that. Also, for this project, high severity of failure outcomes if the project failed. So as a result, the consideration affecting application of quality assurance activities, the decision about the number of quality assurance activities to be applied is affected by project and team factors. As I said you, there's two factors. So in a result, the project factors includes project magnitude, its complexity and difficulty, extent of reusable software components. In example, we check that these factors, and the severity of the outcomes if the project failed, and the other factors, team factors, include its professional qualification as well as acquaintance with the project and related experience. So team projects also include availability of professional support and staff familiarity with team members. These factors are very important for us to effective application of the quality assurance activities. That's all I can talk about this chapter. I hope I talked about that clearly. Hocam bu konu hakkında diyeceklerim bu kadar. Umarım yeteri kadar açıklayabilmişimdir, elimden geldiği kadar maddeleri ve diğer faktörleri açıklamak istedim. İki örnek üzerinde de bunları anlatmak istedim. Dinlediğiniz için teşekkür ederim.
Hello teacher. Our topic for the presentation part 3 is verification, validation and qualification. Three aspects of quality assurance of software product are examined under the rubrics verification, validation and qualification. Industry of Electrical and Electronic Engineers defines the three aspects as follows. Verification, the progress of evaluation a system or component to determine whether the product of a given development piece satisfy the conditions imposed at the start of that phase. Validation, the progress of evaluating a system or component during or at the end of the development progress to determine whether it satisfies specific requirements. Qualification, the progress used to determine whether a system or component is suitable for optional use. According to the Industry of Electrical and Electronic Engineers definition, verification examines the consistency of the products being developed with product developers in previous pieces. When doing so, the examiner follows development progress and assumes that all the former development pieces have been completed correctly, whether as original planned or after removal of all the discovered defect. This assumption forces the examiner to disregard the deviations from the customer's original requirements that might have been introduced during the development progress. Validation represents the customer's interest by examining the extent of completions to his or her original requirements. Commercial validation reviews tend to improve customer satisfaction from the system. Qualification focuses on operational aspects where maintenance is the main issues. A software component that has been developed and documented according to professional standard and style and structure convention procedure is expected to be much easier to maintain than one that provides marvelous coding improvisation yet does not follow known coding style, procedure, and so forth. Planners are required to determine which of these aspects should be examined in each quality assurance activity. There is one example for potential monitoring system. We can see the activity of during of quality assurance and duration of correction and changes per day. We can see the quality assurance activity for all. Thank you for your listening. That was my part.
Hello, my name is Olcay Işık, and this video for a module for software quality assurance, defect removal, effectiveness, and cost. Let's begin. So, the model deals with two quantitative aspects of software quality assurance plan consisting of several defect detection activities. First one is the plan's total effectiveness in removing project defects. The second one is total cost of removal of project defects. And also, the plan itself is to be integrated within the project's development process. We have three data types. First one is defect origin distribution, in which phase did the defect occur. The second one is defect removal effectiveness, how effective are we at removal of defects, that means filtering. The third one is cost of defect removal, how much does cost per defect per phase. In defect removal, all software have some defects. We have to remove them because we don't want defects in our software. When we remove these defects, it have some benefits like time, least cost, etc. I will explain later. Now, the concept of defect removal effectiveness, its measurement are central of software development. As I told you before, the plan itself is to be integrated with the project's development process. Defect removal is one of the top expenses in any software project and greatly affects the schedules. All software has some deadlines. Time is important for us, and also software schedule, it's really important. We have to meet the deadline. Effective defect removal can lead to reductions in the development cycle time and good product quality. These are the important parts. For improvements in quality, productivity, cost, as well as schedule, it's important to use better defect prevention and removal technologies to maximize the effectiveness of the project. It's important for all projects and development organizations to measure effectiveness of their defect removal process. In here, you can see the benefits of defect removal. For example, reduced product cost, improved product quality, increased customer satisfaction time. I think time is really important in here because, as I told you before, we have to meet the deadline. We have to use that time wisely, and reduced development cycle is also integrated with time. The first one is our data is defect origin distribution. Defect origins are distributed throughout the development process, from the project's initiation, its completion. We have some patterns in here. Survey conducted by major software developers such as IBM and TRE, summarized by Boehm and Jones. These Boehm and Jones, these are the really good and sustained have some sustainabilities. In here, you can see software development professionals believe that this pattern hasn't changed sustainability in the last 2 decades. I think this sentence explains the how good this pattern. You can see in here we have a table, a characteristic distribution of software defect origins based on Bohem and Jones. In here we have some software development phases and with their average percentage of defect originating in pace. You can see here coding takes the biggest part with 40%, and in the coding 30% is our coding and 10% is our integration part. The least part is our documentation with 10%. Defect removal effectiveness. In general, we have to talk generally speaking, the percentage of removed defects is lower than the percentage of detected defects because some corrections are ineffective or inadequate. Others, undetected and uncorrected, are passed to successive development phase. As I told you before, our plan is integrated within the project development phases. We have to detect and correct the defects in each phase. When we didn't do that, our defects go through our the other development phases, and that would be a problem for us. It's assumed that any quality assurance activity filters a certain percentage of existing defects. It should be noted that in the most cases, the percentage of removed defects is somewhat lower than the percentage of detected defects, as some corrections, about 10% according to Jones, for example, are inactive or inadequate. Defect removal effectiveness, the remaining defects, those undetected or uncorrected, are passed to successive development phases, as I told you before. And also, these defects, those undetected or uncorrected, goes to our other phases. And in these phases, these defects combine with other defects, and that combination is show us the new defects. For example, after previous quality assurance activities together with new defects created with current development phase, it's assumed that the filtering effectiveness of accumulated defects of each quality assurance activity is not less than 40%. In here, we have a table with quality assurance activity combined with average defect filtering effectiveness, right? As you can see here, code inspection is take the biggest part, as before, the 65%, and that comes from the design inspection with 60%, and the last one is unit test after code inspection with 30%. In here we have a cost removal. The cost of defect removal is calculated by multiplying the number of defects removed by the relative cost of removing defect. Defect passed to the customer will be detected by him or her. Their full removal at this pace will occur heavy cost. The model allows the calculated estimates of the cost of decisions regarding the quality assurance plan. Costs are much greater in later development phases. Data collected about the development project costs show that the cost of removal of detected defects varies by development phase, while costs rise sustainability as the development process proceeds. For example, removal of a design defect detected in the design phase may require an investment of 2.5 working days. Removal of the same defect may occur 40 working days during the accepted test. That is a really big difference. Several surveys carried out by IBM, TRV, GTA, Bohem, and others, summarized by Bohem, estimate the relative cost of correcting errors at each development phase. Now we can check the table. In this table, we have the software development pace combined with average relative defect cost. In here, you can see the cost units of each paces. For example, in unit test takes the 6.5 unit cost unit, but in operation by customer after release take 110 cost units. It's a really big number. The model is based on the following assumptions. The development process is linear and sequential, following the waterfall model. In waterfall model is too linear. When you make mistake in last phases, for example, or some phases, you can't backward to before phase that did it before. You have to go to first phase, and you can, and then you will. You have to correct the errors, and you can go on because its waterfall model is too linear and sequential. The number of new defects are introduced in each development phase for their distributions. This table is the same as the our first table. I put it here because I want to show the clearly average percentage of defect originating in each phase. Review and test software quality assurance activities serve as filters, removing a percentage of the inherent defects and letting the rest pass to the next development phase. For example, if the number of incoming defects is 30 and the filtering efficiency is 60%, then 18 defects will be removed while 12 defects will remain and pass to detected by the next quality assurance activity. Typical filtering effectiveness rate of various quality assurance activities shown in the table. You can see the effectiveness rate. I will show you. I already showed you before. Sorry. As you can see here, code inspection takes the biggest part as before. The cost of defect removal is calculated for each quality assurance activity by multiplying the number of defects removed by the relative cost of removing defect. That will show us the cost units. I already showed you this table. I put it here because I want to show you again clearly. The remaining defects that we didn't undetected or we didn't correct it. Unfortunately, pass it to our customer and will be defected by him or her. In these circumstances, full removal entails the heaviest of defect removal cost. In here, you can see the 110. It's really big number, as I told you before, for cost units. In here, in the model, each of quality assurance activities represented by a filter unit, as shown for design in figure. The model represents following quantities. The first one is pace originated defect. The second one is passive defects from the former paces. As I told you before, when sometimes we can't detect the defects or uncorrect the defects, and these defects goes through our next phases. The third one is filtering effectiveness. The fourth one is removed defects. Fifth one is cost of defect removal. The last one is total removal cost. In here, you can see the our phases and their steps. For example, cost reduction or etc. And also in this table actually is a combination of two tables. You can see the quality assurance activity. you can see the defect removal efficiencies and cost of removing detect cost units. For example, when we check the operation pace that takes the biggest part, defect removal effectiveness is 100%, but the cost of units is 140. In requirement specification review, take the least cost with 1, and defect removal effectiveness is 50%. Other than operation pace, takes the 50% of defect removal effectiveness. We have a comprehensive quality assurance plan, and actually the comprehensive plan as a whole is much more economical than the standard plan, as it saves 41% of the total resources investing in defect removal compared with the standard plan. Compared to the standard plan, the comprehensive plan makes a greater contribution to customer satisfaction by drastically reducing the rate of defect detected during the regular operations, 6.9% to 2.6%. And also, this plan achieves the following. First one is adds 2 quality assurance activities, so that 2 are performed in the design phase as well as in the coding phase. The second one is improves the filtering effectiveness of other quality assurance activities. In here, you can see actually detect defect removal effectiveness and the cost of removal detect defect. Operation pace, as the same before, takes the biggest part, and requirement specification review takes the cost units with 1, as same as before. Defect removal effectiveness is in here 60%. But in here you can see the 50%, but in here 60%. I will combine this. I already combined the comprehensive quality assurance plan and the standard plan. I will show you the table later, and I will explain it with details. The standard plan successfully removes only the 57.6%. That means 28.8 defects out of 50. Of these defects originated in the requirements and design phase compared to 90.2%. For the comprehensive plan, before coding begins, this is to be expected as direct result of more intensive defect removal efforts that characterize the comprehensive plan. You can see here our comparison table, standard plan and comprehensive plan. For example, in here, requirement specification review percentage of removed defects is 7.5, but in comprehensive plan is larger, 90 point. Cost of removed defects, that means cost units, 7.5. In here larger, it's 9. But when we check the total for internal quality assurance activities, standard plan for percentage of removed defects takes the 93.1%. Cost units takes the 1014.3. Percentage of removed defects is larger than the standard plan with 97.4%. Cost of removed defect is smaller than the standard plan, 76.4. The total percentage of removed defects is same. It has to be same. We have to remove all the defects in our software, but the cost is efficiently smaller than the standard plan. In standard plan, 1,773.3, but in comprehensive plan, 1,046.4. We have a summary part in here. In summary, the model deals with two quantitative aspects of software quality assurance plan designed for a specific project. One of them is total effectiveness to defect removal. The second one is total cost of removal. And also, our model is based on the following assumptions. Based on development process with waterfall model, sorry. The number of new defects are introduced in each development phase. Various review and test software assurance activities serve as filters, removing a percentage of inherent defects, while allowing the rest to pass to next software assurance activity. The cost of defect removal is calculated by multiplying the number of defects removed by the relative cost of removal project. These are the important sentences actually in my presentation. Incoming defects are the sum of the defects passed from the former quality assurance activity together with new defects created in the current development phase, as I told you before. The model allows to calculate estimates the cost of decision regarding to quality assurance plans. Addition or elimination of the quality assurance activity from a given plan. Defects passed to the customer will be defected by him or her will occur a heavy cost. Application of current quality assurance procedures, activity versus application of more efficient yet more costly procedure. Utilizations of the model thus enables the comparisons of software quality assurance policies and activity plans. Thank you for listening. That's all for me. Have a good day.